last but not least, joining us live from the United States, Professor Sam Coogan will present his research on formal probabilistic guarantees for safe learning in autonomous systems. Professor Coogan is an assistant professor at Georgia Tech with a joint appointment in the School of Electrical and Computer Engineering and the School of Civil and Environmental Engineering. His research is in the area of dynamical systems and autonomy and focuses on developing scalable tools for verification and control of network, cyber-physical systems, with an emphasis on transportation systems. Saying all that, please join me welcoming Professor Coogan.
So today I'm going to talk about certifying robustness in neural networks, a mixed monotone approach. This is actually slightly different than what I suggested I would talk about when I first submitted my abstract and title for this presentation, and it's because I got pretty excited about a brand new result we have. So I'm going to talk about this brand new result, which is a little different than what I had suggested originally. First, I want to start by acknowledging my tremendous collaborators on this work. So first, Saber Jafarpour, who is my new postdoc. Prior to that, he was a postdoc with Francesco Bullo and helped initiate this connection. My student Matt Abate, and then Francesco Bullo at UC Santa Barbara, and his student Sasha Davidov. And so what I'm going to talk about today is this paper we have up on the archive about robustness certificates for implicit neural networks. So if whatever I say today doesn't make sense, or I don't have enough details, or whatever, you can go to this paper on archive and find all the details there. Good. So let me just begin by describing the problem that we're interested in studying. And it's this well-known problem that's become more and more prevalent over the past 6 or 7 years, I guess, is that neural networks can be brittle. So here's an example. We have a digit. This is from the MNIST dataset of handwritten digits. Clearly, this is a digit that's a 6. Any human would be able to identify this digit. But there's this commonly known problem that you can add a little bit of perturbation. So this perturbation is represented here with this lower image. It's just a small perturbation to every pixel. Here it's magnified just to accentuate the perturbation, but it's actually quite a small pixel variation. It's cleverly designed. These are so-called adversarial perturbations, but you put a little bit of perturbation in the image. A human would still clearly see this as a 6, but it goes through your neural networks. For example, you might get a label of a 4 at the end, right? And these are actually not just numerical quirks. They're repeatable. They transfer across networks. You can different neural networks train for the same adversary. So this is in some sense a real problem in neural network training. And so there's been increased interest in understanding A, what the problem is, and B, how we can create neural networks that are robust to these types of perturbations. Okay. So what can we do when we study these perturbations? Well, I'm just going to highlight 2 points here. The first is that you have to settle on a norm. When you say that you have a perturbation that's small, you have to define what you mean by small here. And believe it or not, this is a little bit more nuanced than it may seem at first. I think it's becoming clearer and clearer that the correct norm to be studying these perturbations in is the infinity norm, which measures sort of max pixel differences, right? So for example, you might be more familiar with the 2 norm. The 2 norm would somehow create a ball of pixels that squares every pixel density and things like this. And that's typically not what we would typically consider to be a close image. So max pixel difference seems to make a lot more sense, at least in image recognition problems. So there's this sort of recognition that L infinity norms are more appropriate. And in very high dimensional spaces, an L infinity norm can actually behave quite differently than an L2 norm. So your choice of norm actually does make a substantial difference in the kinds of results you get. The other point that I'm going to try to make today is that, there's been kind of an increasing body of literature in the past 2 years, say 3 years, that study global Lipschitz constants of neural networks as a means to help train against these robust adversaries. And I'm going to try to make this argument that, global Lipschitz constants may not be the right approach. It may make much more sense to focus on local properties. And this is just a very kind of simple cartoon example. Suppose you have 3 training points and you're trying to fit a function through these 3 training points. Maybe this is a classification problem or something like this. You might have some nominal function fitting that looks like the blue function. The problem here is it's not very robust at this input. If you just adjust a little bit to say -2 or +2 or something like this, then your function outputs a very different value. So one might say this is not particularly robust at 0. A a method that would seek to limit the global Lipschitz constant might produce something like the red plot here. And so certainly there's less variation. The slope of this function changes, has a less the maximum value of the slope is smaller, but it doesn't even pass through these training points. And so it's not a great classifier. So you lose some what we would call kind of the clean performance of this function. So maybe this green function is a better type of function you would want. Maybe we would consider this to be more robust, at least at these training points, because it gets nice and flat at the training points. Now, its Lipschitz constant is actually probably larger than the blue function, or it's certainly larger than the blue function because it gets steeper in some places. But near these training points, near the categories you're trying to classify, it gets nice and shallow, which would imply this robustness. So I'm going to try to make this point also today that these local properties might be the more appropriate method for thinking about robustness of these neural networks. Okay, so that's the challenge. How do we certify robustness of neural networks? I'm going to do a few things in this talk. First, I'm going to focus on a particular type of neural network called implicit neural networks. You may or may not have ever heard of these. They're kind of new, but they're getting a lot of buzz in certain pockets of the machine learning community as being a very general class of systems of neural networks that have some nice analytic properties. It makes it a little bit easier for us to study them, especially from a dynamical systems perspective, which is what I'm going to advocate for today. Then I'm going to introduce this tool called mixed monotonicity. We use it in my lab a lot for reachability and high dimensional nonlinear dynamical systems. This is the first time we've applied it to this problem of neural networks, but I'm going to argue that it's the right kind of tool to do exactly what I was suggesting on the previous slide. And so we'll apply that tool for this, what we can think of as like an input dependent certified robustness, as opposed to this global Lipschitz property. We can talk about robustness locally at certain points of the state space. And then I'll just show some plots from this MNIST handwriting example, this handwriting digits example. So again, let me dive in a little bit and describe this class of networks called implicit neural networks. They were introduced just a few years ago by Zico Coulter and co-authors in this citation down here, this NeurIPS paper down here. There's also a paper by El Gawi and co-authors recently published that sort of studied the same thing from a slightly different perspective. But the setting is kind of the familiar neural network setting. There's an input, we'll call it U. For example, this might be the pixels of an image, a fairly large dimensional. There's an output vector Y. For example, this might be a classification vector, and this is typically lower dimensional. And then sort of the secret sauce of implicit neural networks is instead of passing this input through a bunch of feed-forward layers that each generates a hidden variable vector, right? And then you stack these and you try to get creative in how you do these layers. We can put everything into one implicit layer. And that's represented here with this equation that this x, this is our hidden variable, will be equal to some nonlinear function of an affine transformation of a of x, of x and u, the input and the hidden variable. So the unusual thing here is this is an implicit equation. X appears both on the left and on the right. I'm going to show in the next slide that this is in fact a generalization of sort of standard feed-forward networks, and we'll see throughout the talk that this particular form is especially amenable to a dynamical systems perspective, which is why me and my collaborators have gotten so excited about this particular class of networks. So again, X is our usual hidden variable, just like it would be in a classic feed-forward network, but here it's just defined by this implicit equation. And then A, B, C are these tunable weight parameters. These are the nonlinear, the linearity piece of the neural network. And then phi, this is just our usual element-wise scalar nonlinear activation function. So like a ReLU or a hyperbolic tangent, something like this. And all we need for this function is that it's weakly increasing and has slope less than or equal to 1, which is satisfied by most of these sort of standard nonlinear activation functions. Okay. So let me just make a few basic observations about implicit neural networks. The first is these may appear to be more restrictive because I can't nest these equations. I just have one implicit equation, but in reality, this actually encompasses more general feed-forward networks because I can stack them up essentially and make one large implicit equation that actually isn't really implicit. It contains my feed-forward network. So let me just show how that can be done. Suppose you have what we might consider a standard feed-forward network where some output Y is maybe some A of L times some hidden variable X sub L. That's the last layer of the feed-forward network. And then each of these layers is defined in this feed-forward way where the output of layer L plus 1 is equal to some nonlinear function phi of sub L times or of A sub L x sub L, right? So this is just kind of a classic feed-forward network. You take a linear matrix multiplication, and then you do some nonlinear activation. And you start with the input image U as your first input to the network. Well, I can actually rewrite this equation in an implicit form. It really doesn't have this implicit computation structure, but I can write it as an implicit equation simply by stacking all of my hidden variables x1 through xl, and then creating this sort of it's almost it's a matrix with a diagonal on the just on an upper diagonal piece of this, where I stack all of my weight matrices, my A weight matrices, and then my input vector just has the activation for the input image U, and then my output Y has this particular structure as well. And so you can see, if you just do the carry out the arithmetic here, this actually recovers our feed-forward network. So my first observation about implicit neural networks is that they're actually more general than feed-forward networks. I can take any feed-forward network and rewrite it as an implicit equation, but I can of course do more than that by making these this matrix a dense matrix instead of this upper diagonal matrix, for example. My second observation about implicit neural networks is that even though they're more general, well, it's not my observation, these are observations made in these papers, even though this is more general class of networks, we have a new problem. The problem is that since these are defined with an implicit equation, we have to be careful about whether or not there even exists, and if there does, is it a unique solution for this hidden variable x. So you see it's an implicit equation, so in general, this may have many solutions, it may have no solutions. So we have to be more careful with that than we do in a classic feed-forward case. And the typical way to do this is you have to impose restrictions on the A matrix in particular. So it's this A matrix that determines whether or not, assuming you have a fixed nonlinear activation function, it's the A matrix that determines whether or not you have a unique solution, whether it exists. And there's several classes of A matrices one could assume that would give you uniqueness and existence here. So for example, in this paper by Winston and Coulter in 2020, they proposed this sort of LMI condition on the A matrix, basically ensuring that it's got some semi-definite properties to it that ensures existence and uniqueness of this implicit equation. El-Gawi imposes a different restriction on A, namely that its infinity norm is less than 1, and then Jaffarpour and co-authors, this includes some of the co-authors on this paper, showed in a very recent NURBS paper that in fact you can substantially improve this infinity norm property by looking at the matrix measure of A instead of its induced matrix norm. And the matrix measure, it's got a deep, rich theory behind this particular quantity. I won't have a chance to go down that path. I'm simply going to observe that the matrix measure, the infinity matrix measure of a matrix A, which is defined to be sort of this instantaneous, it's the derivative in the direction of A of the induced infinity norm at the identity matrix. So that's how you would define this matrix measure, and has this very easy equation that it's this maximum row sum where I put absolute values on the off-diagonal entries of A, but I leave A as is. So in particular, I can have negative entries on the A, on the diagonal, and I can actually get a negative number for this matrix measure. So one key feature of the matrix measure is it can take on negative quantities, and in general, it's much less restrictive than this infinity norm on A. So these are just some choices for a condition that would give you uniqueness, existence and uniqueness for this implicit equation. And what we're going to use is we're going to focus on this matrix measure condition down here, which becomes key for us. So let me just rewrite this a little bit. Let me introduce a little notation. I'm going to make heavy use of this notation called the Metzlerization, or we call it the Metzlerization of the A matrix. A Metzler matrix is just a matrix where all the off-diagonal entries are non-negative. So if I give you a general A matrix, its Metzlerization means we just take the absolute value of every off-diagonal entry. We leave the diagonal entries alone, but we just take absolute values of these off-diagonal pieces, and then we'll use this these lower brackets to be what we can think of as the complement of the Metzlerization. So it's just the difference, A minus its Metzlerization, okay? And then with this notation, a convenient, compact way of writing the infinity matrix measure of a matrix is just to be the maximum entry of this product between the Metzlerization of a matrix and and this ones vector, right? I could just, this is just a vector, and then I look at its maximum entry, and that becomes the matrix measure. Okay. Good. So now that I've introduced this concept of implicit neural networks, let me just turn back to this problem of certifying robustness a bit. Suppose I have an input U, this is again an image, and an output Y, which is, for example, the confidence of the digits or something like this, and some implicit neural network classifier. And suppose we make a classification decision by just simply looking at the maximum entry of this vector. And we'll call that I, that's its classification. And suppose it has some true classification. We'll say that the classifier is L infinity adversarial robust with a certain amplitude epsilon at this particular point U. If no matter what perturbation I add to this image, so long as that perturbation has infinity norm less than epsilon, the classification you get is the true classification, right? So this is the desirable property that we want. There's a couple ways we can analyze this robustness property. For example, as I alluded to at the beginning of the talk, I can look at the Lipschitz constant. If I had a global Lipschitz constant for the system, I could use that to verify sort of the maximum distance between a classification at a particular input and a classification at a nearby input. So for example, in Jafarpour et al., they use this matrix measure to produce a global Lipschitz constant for the network. And you can use this to certify robustness. So instead, though, what we're going to do in this talk is propose an input-dependent bound that bounds the output given a priori bounds on the input. So if I know that my input image lives within some hyperrectangle of the input space, so this is the notation I use for that, then what I want to do is I want to find some hyperrectangle in the output space that's guaranteed to contain my classification output, for example. It's a little bit mathematically simpler, instead of thinking about the output space Y in these implicit neural networks, to instead think about this implicit hidden variable X, and then it's easy to go from implicit variable X to the output. Really, all of the magic happens in bounding this hidden variable X based on a bound on the input U. And so that's what we're going to do. We're going to look for this a bound on X of U, which is the solution to this implicit equation using bounds on the inputs. And what we're going to do is we're going to use mixed monotonicity for this. And then we're going to show that this matrix measure contraction condition is well posed, implies a well posedness of a certain mixed monotone fixed point equation. And then we're going to see how we can use this to guarantee convergence of the appropriate fixed point computation. Good. So the first thing I'm going to do, and this is, as I alluded to, is the reason why we like these implicit neural networks, is I can exchange this fixed point equation. So here's my original fixed point equation. I can exchange this for a dynamical system. So of course, this is just an obvious observation. X is a solution to this fixed point equation if and only if, sorry, this shouldn't be X equals 0. If and only if X is an equilibrium of this dynamical equation, X dot is equal to negative X plus phi AX plus BU, right? This is just some simple arithmetic, but now I can think of a dynamical system that has these dynamics, and I can try to think about whether or not it has an equilibrium point, and whether or not that equilibrium point is robust perturbations in U, et cetera. And so that's the perspective we're going to take in this talk. So I can equivalently state my goal from the previous slide is I want to find some hyperrectangle X under bar and X over bar, which depends on sort of the perturbations of the input, that is robustly forward invariant for this dynamical system. That means that the trajectory of this dynamical system never leaves that box, regardless of what this input U is, okay? And if I can find that box, I can use that to create, I can use that to quantify my adversarial robustness of my neural network. Turns out that the mixed monotonicity, which is this tool I'll define on the next slide, is very well suited exactly for this task, for finding robustly forward invariant boxes based on a box constraint on some disturbance, which in this case is the input image U. Okay, so let me define very quickly what a mixed monotone dynamical system is. In fact, I talked about this class of systems last year at this conference, so I'll just try to very quickly give you the definition. If you want more details, I have a tutorial paper you can find from a CDC a couple years ago. But this definition is general. It doesn't apply just to implicit neural networks. A dynamical system X dot equals f of X comma U with some input U is mixed monotone with respect to what we'll call a decomposition function D, if for every I, you have the following properties. So first, the decomposition function accepts as arguments pairs of states, X, and hat, and pairs of inputs, u and u hat. You needed to recover the vector field f if I substitute in the same value for that pair of states and the same value for the pair of inputs. And it also needs to have some monotonicity properties, where it's increasing essentially in these unhatted variables, and it's decreasing in the hatted variables. There's a slight caveat there where I only want to consider x less than or equal to y, where I freeze the ith entry of xi and yi. And if you're familiar with monotone dynamical systems, this caveat here will seem familiar. And in this way, mixed monotone systems generalize this class of monotone dynamical systems. But this is just a definition. And it'll turn out, if we've shown a few things over the years. First, every system that has Lipschitz f has at least one decomposition function. And in general, there are many decomposition functions. The caveat is these are typically difficult to find in closed form. It's kind of like searching for a Lyapunov function. You might know that there is one, but it can be hard to find it. It depends on some domain-specific knowledge, et cetera. What's really phenomenal, what makes me so excited about this particular result I'm talking about, is that implicit neural networks, they happen to have a very natural decomposition function, and it's the best you can get. It happens to be the best decomposition function that you can find, and we have ways of proving that using this mixed monotone tools. And so that's why these tools just blend so well for this problem of neural network robustness. The key to mixed monotone systems, sorry, I'm trying to move fast so that we finish on time, is that I can use the decomposition function to create a larger dynamical system. If my original system had n states, this new system has 2 n states. We call it the embedding system, and we define it in this somewhat peculiar way, where we define x dot dynamics and x hat dynamics in terms of this decomposition function d, and then we do this operation where we swap x and x hats, and then we swap, say, some fixed lower bounds, u underbar and u overbar. So these underbar and overbar inputs, for example, are known bounds on our, say, input image that we're trying to determine. Turns out, I talked about this a year ago, these embedding dynamics have a very specific property. They are monotone. It's a monotone dynamical system, but with respect to this very special order relationship, which we can call the southeast order. It's now defined on 2n dimensions. X hat is less than or equal to, with respect to the southeast order, y hat, if and only if x is less than or equal to y. This is in element wise, and x hat is greater than or equal to y hat. This is element wise. Okay. Really, what this buys us is this theorem we proved a couple years ago, that if you give me some particular fixed inputs, u underbar and u overbar, and if I can find an equilibrium point in this higher order embedding system, then this equilibrium point defines a rectangle with points x equilibrium and x hat equilibrium that is robustly forward invariant for this original system. This is exactly what we want. We want to find a robustly forward invariant hyperrectangle, regardless of this input, that might live in this uncertain set u underbar and u overbar. Good. So how are we using that result in this implicit neural network? So let me summarize our main results for these implicit neural networks. So the next 2 slides will have our main results of this archive paper. The first result is that we can construct a decomposition function, and in fact, it's the best decomposition function for our implicit neural network dynamical system. That's this x dot equals negative x plus phi ax plus bu. I can define the best decomposition function for this system in a very natural way. I just define it to be equal to, this should be negative x plus phi. So I swapped the negative variable here, but this is negative x plus phi, and then all I have to do is I split apart the A matrix with its Metzlerization and the complement of its Metzlerization, and then I associate the Metzler version of A with x, and this complement Metzler version of A with x hat, and then I separate out B with its positive entries and its negative entries, okay? And then if I use this definition of D in my embedding system, I'll get the following embedding system written down here. This is a 2n-dimensional system where it has an x underbar and an x overbar. And these become, you can think of these as the dynamics of for a lower corner and an upper corner of a rectangle, okay? And I just plug in my expression for my decomposition here, and I get this embedding system. This is the embedding system. And I have this property that if my input lives within some hyperrectangle, u underbar and u overbar, then the solution to my implicit neural network, implicit layer, is sandwiched between within a hyperrectangle with 2 corners, a lower corner and upper corner, defined by the equilibrium of this embedding system here. So that's the first major result. The second major result is that this exact same matrix measure condition that ensured well-posedness of the original INN to begin with ensures that this mixed monotone embedding system has an asymptotically stable equilibrium point for any pair of inputs, U underbar and U overbar. Then also just from a numerical perspective, if I take a small enough discretization step, an Euler forward Euler discretization of this equation will get me to this equilibrium point. So I can compute this robust hyperrectangle that I'm after. Good. So here's just a very simple 2D example, just to kind of give a picture. So here's the numerics here. It's a ReLU example. This is simple enough that I can discretize all of the inputs, and I can kind of get this, let's say, yellow rhombus-looking thing in the middle. This is my true sort of classification set that I'm trying to over-approximate. And then I have successive approximations, red, green, and blue. Red is if I use a Lipschitz bound. Green is if I use this method that was very recently proposed in this ICLR paper that uses interval bound propagation. So it's better, much better than the red. But then blue is our method. So blue gives us a much better approximation for this example. So this is just a simple 2D example. We've applied this to the MNIST handwriting dataset. And if you're not familiar with this, this is a large, several tens of thousands database of images of handwriting samples, black and white images, and the goal is to classify them as one of the digits 0 through 9. And so I can do this, and then I can test this certified robustness using our mixed monotone approach. This is the amplitude of the perturbation I'm trying to certify robustness against. This is my certified robust accuracy. The green plot is what I would get if I use sort of the prior state of the art, these Lipschitz bounds. And then the orange and the blue methods are what I use if I use my mixed monotone methods. And in fact, the difference between these two, there's a subtle difference. We can even do a slightly better transformation to get something slightly better. That gets us from the orange to the blue, and I'll just leave that for the paper. But the point is that this curve much better certified robust accuracy than the Lipschitz bounds that we were after. And the reason, again, for this is severalfold, but one of them is that we're really focusing on bounding the test inputs as opposed to bounding a global constant over the whole neural network. The plot on the right just shows the kind of accuracy you get if you actually apply sort of these state-of-the-art adversarial attacks, projected gradient descent, and what is this FGSM method to these examples. The point of this plot is to show that even though we're doing much better with mixed monotonicity, there still seems to be quite a large gap between what we can certify and what we can actually exhibit using state-of-the-art adversarial perturbation methods. So notice the factor of 10 difference in scaling between these axes as well. But again, we have ideas on how to push the envelope there. So I'm already over time. So let me just summarize with some concluding thoughts. Mixed monotonicity, I'm positioning is a very natural lens for studying robustness of neural networks and of implicit neural networks in particular. Part of the reason for that is it deals very well with hyperrectangles. Hyperrectangles are exactly what you want to use when you're talking about robustness with respect to, for example, pixel perturbations in an image. State-of-the-art conditions for the well-posedness of implicit neural networks also for free implies well-posedness of the robustness bounds for the mixed monotone embedding system. So there's no new conditioning you have to apply to the system to get the kinds of bounds that we're getting for these results. And then the next steps are to apply these methods for training of neural networks. And we're working on that, and we're about to submit a paper on that. So I want to, again, thank my co-authors who have done a tremendous amount of good work here and are coming up with lots of creative ideas for applying these methods. And again, this is a paper that's an archive if you want to take a look. So sorry, I used up all of my time, but I'll end there.
Thank you very much. Do we have questions?
Hello. Oh, thank you for the nice talk. So when you talk about the existence of the solution, how do you deal with the function phi? It can be an activation function, as you mentioned at the beginning, but this may induce some discontinuities. As an activation function, it may induce some discontinuities. And this will affect the existence of the solution in the sense of Filipov sense. So I think you get what I mean there. So what about the existence of the solution if you have in presence of discontinuities that is coming with this activation function, and how do you deal with that with the matrix measure and with the robustness certification?
Sure. Yeah.
Thank
of
you.
course. Yeah. Thanks for the question. So this is a nonlinear activation function. We do assume it's a continuous function. So we kind of make this classic assumption in the neural network literature that this is a continuous activation function. It may not be continuously differentiable, like the ReLU function is not differentiable at the origin. But that lack of differentiability doesn't affect it does not affect either the fixed point equation nor sort of this dynamical systems interpretation of that. So so that's fine. We still get well-behaved solutions to the fixed point equation and to the dynamical system. So I guess in short, we don't consider discontinuous activation functions, but I think that that's fairly standard in the neural network literature for these networks.
Thank you very much.
Thank you for the invitation.